Welcome to the tutorial series on Basic Electrical Engineering Made Simple. In this series, we shall take up basic circuit concepts and discuss about Kirchhoff's laws. Friends, do you know that Gustav Robert Kirchhoff lived during the period 1824 to 1887. He was a German physicist who contributed to the fundamental understanding of electrical circuits, spectroscopy, and the emission of black body radiation by heated objects. And you will be surprised to know that he formulated the electrical circuit laws in 1845 while he was still a student. These laws now are known as Kirchhoff's laws and are widely used in electrical engineering. Kirchhoff formulated two electrical circuit laws. One is known as Kirchhoff's current law and the other is known as Kirchhoff's voltage law. First, let us take up Kirchhoff's current law. And basically, you should know that the Kirchhoff's current law is applied to a junction point in the network. When I say it is applied to a junction point in a network, in a given network, you should be in a position to identify the junctions, the branches, and the loops correctly. For example, consider a network shown in figure. If I ask you how many junctions are there in this network, your answer should be 5. And they are A, B, C, D, and E. If I ask you how many branches are there in the network, your answer should be 8 and they are AB, AC, AD, AE and BC, CD, DE and AB. Similarly, if I ask you how many independent loops are there in this network, your answer should be 4 and they are ABCA, ACBA, ADEA and AEBA. If you understand these aspects correctly, you will be in a position to understand the Kirchhoff's laws clearly. To understand the Kirchhoff's current law, consider the same network shown in figure and you see that the junction A and the branches connected to that junction A are extracted as shown in figure. And you will see that the branches are shown as straight lines connecting the junctions and capital I1, capital I2, capital I3 and capital I4 are the respective branch currents. Friends, the Kirchhoff's current law can be stated in two forms. The first statement says that the sum of the currents flowing towards the junction point is equal to sum of the currents flowing away from the junction point. If we put this statement into an equation, we get I1 is equal to I2 plus I3 plus I4 because I1 is coming towards the junction and I2, I3 and I4 are flowing away from the junction point. Similarly, the second statement says that the algebraic sum of the currents meeting at a junction point is equal to 0. When we say algebraic sum, we have to assign this sign for the direction of the current. and we assign the current flowing towards the junction point as positive and the current flowing away from the junction point as a negative. So according to this assignment, the algebraic sum of the currents meeting at a junction point yield the equation 2, and it says that I1 minus I2 minus I3 minus I4 is equal to 0. And you must note that the equation 1, according to simple algebra, can be obtained by transferring I2, I3 and I4 to the left side of the equal sign, and you get equation 2. And that is very simple. Friends, let's now consider Kirchhoff's voltage law. Basically, you must understand that the Kirchhoff's voltage law is applied to a closed loop or mesh or between any two nodes of the network. Now, to formulate the concept of voltage rise and voltage drop, let us use a simple circuit and the Ohm's law that we have learnt already. So, in figure shown, we have taken a voltage source connected across the resistance, and we know according to Ohm's law, I is equal to V by R, or V is equal to I into R, or V minus IR is equal to 0. So this simple equation obtained using Ohm's law for a single loop will give us the idea of identifying the voltage rise and a voltage drop. Now in the equation V minus IR is equal to 0, you see that the voltage V is taken as positive, which means if we trace the active element from negative to positive, there will be a voltage rise, and the voltage rise is taken as positive. And if we trace the active element from positive to negative, there will be a voltage drop, and the drop is taken as negative. Similarly, in the equation V minus IR is equal to 0, we have taken minus I into R. It means while tracing the passive element like resistance, if we trace the PD in the direction of current, there will be a voltage drop and it is to be taken as negative. And similarly, if we trace the PD across the passive element against the direction of current, there will be a voltage rise and it is to be taken as positive. So, don't you feel that a simple circuit and Ohm's law give us the concept of the voltage rise and a voltage drop, and we are going to use this concept in writing the Kirchhoff's voltage equation. Friends, first let us define the statement of Kirchhoff's voltage law. The Kirchhoff's voltage law states that the algebraic sum of the potential differences in a closed loop is equal to 0. When we say the algebraic sum of the potential differences, we should be in a position to identify the voltage rise or voltage drop across each circuit element, and by suitable assignment, we should be able to write the Kirchhoff's voltage equation. So, consider the figure shown in 1 and in figure 2. You see that the applied voltage is of the same polarity in both the circuits, whereas the current is assumed to flow in the clockwise direction in figure 1, and it is assumed to flow in the anti-clockwise direction in figure 2. Now, Using the concept of voltage drop and voltage rise, we can write the Kirchhoff's voltage equation tracing the circuit in the clockwise direction. Consider figure 1 tracing the circuit in the direction C, D, A, B, C. We get V minus I into R is equal to 0. It is V or plus V because we are tracing the active element voltage source from negative to positive. Therefore, we have taken plus V. We have taken the potential across the resistance I into R as a negative because we are tracing the potential difference in the direction of the current, that is from A to B. Therefore, we have taken minus I into R. From this equation, we get I is equal to V divided by R. Similarly, tracing figure 2, again in the clockwise direction, say C, D, A, B, C, we get plus V plus IR is equal to 0. It is plus V because we are tracing from C to B or from minus to plus across the active circuit element. Therefore, we have taken plus V. Similarly, we are tracing from A to B or in the direction against the direction of the current. Therefore, we have taken the potential across R as plus IR. Therefore, we get the equation for I equal to minus V by R. What does this mean? When we write the Kirchhoff's voltage equation and find the equation for the current, if we get a negative answer, the meaning is the true current is in a direction opposite to that of the assumed current. It means in the circuit shown in figure 1 and in figure 2, the true current will flow in the clockwise direction. If you understand this, definitely you will be able to write the Kirchhoff's voltage equation of any complex network. Friends, do you have a question in your mind that is it necessary to trace the circuit only in the clockwise direction? Absolutely no. You can assume the branch currents arbitrarily and you can trace the circuit either in the clockwise direction or in the anti-clockwise direction. The result should be same. For example, consider the same circuits that we have taken earlier and write the Kirchhoff's voltage equation by tracing the circuits in the anti-clockwise direction. So, if we write the Kirchhoff's voltage equation for the circuit shown in figure 1, tracing it in the anti-clockwise direction, we get minus V plus IR is equal to 0, and from which we get I is equal to V divided by R, and you see that the result is the same as that we have got in the earlier discussion. Similarly, if we trace figure 2 again in the anti-clockwise direction, we get minus V minus IR is equal to 0, from which we get I is equal to minus V by R, which the result is same as we have got earlier. Therefore, you must understand that you can assume the direction of branch current in any direction you want, and you can trace the circuit either in the clockwise direction or in the anti-clockwise direction, but be clear to identify whether there is a voltage rise or voltage drop across each element, and if this concept is clear, I don't think that you can err in writing any Kirchhoff's voltage equation for any complicated loop of a circuit. Friends, let me summarize the discussion that we had till now. In a nutshell, we can say that the Kirchhoff's current law is applied to a junction point in a network. Current law can be stated in two ways. One, the sum of the currents flowing towards the junction point is equal to sum of the currents flowing away from the junction point. The second statement states that the algebraic sum of the currents meeting at a junction point is equal to 0. When we say the algebraic sum, you must understand that the branches are connected to a junction point and the currents that you assume are the branch currents. So keeping this in mind and assigning the sign for the current flowing towards the junction point and current flowing away from the junction point, you can write the equation for the statement 2. Similarly, the Kirchhoff's voltage law is applied to a closed loop or mesh or between any 2 points in a network. It states that the algebraic sum of the potential differences in a closed loop is equal to 0. While writing the Kirchhoff's voltage equation, we have to identify the voltage rise and voltage drop and assign the sign for the potential differences. If we trace the PD across active element from negative to positive, take PD as positive. From positive to negative, take PD as negative. In case of the passive element, if we trace the PD in the direction of current, the PD is taken as negative, and if we trace the PD against the direction of current, the PD is taken as positive. So keeping these assignments for the currents, for the potential differences, you can write the Kirchhoff's voltage equation very easily. And remember, the current in the circuit can be assumed arbitrarily. While writing the Kirchhoff's voltage equation, the circuit can either be traced in the clockwise direction or it can be traced in the anti-clockwise direction. The result obtained will be same. Hope you understand these concepts very clearly and you are confident in writing the Kirchhoff's equations correctly for a given network, for which we will consider a simple example and write the Kirchhoff's voltage equations in the next discussion. Friends, let's take a very simple example wherein we are required to write the Kirchhoff's current equations for the junctions B, C, D and E and the Kirchhoff's voltage equations for the loops ABCA, ACDA, ADEA and AEBA. To write the Kirchhoff's current equation, let us assign the sign. The current flowing towards the junction point is taken as positive. The current flowing away from the junction point is taken as negative. So with these assignments, if we write the Kirchhoff's current equation for junction B, we get I minus I1 minus I5 is equal to 0. For junction C, we get I5 plus I2 minus I6 equal to 0. And for junction D, we get I6 plus I3 minus I7 is equal to 0. And finally, for junction E, we get I7 plus I4 minus I is equal to 0. To write the Kirchhoff's voltage equation for the loops, we have assigned that if we trace the active element from negative to positive, the rise is taken as positive, and if we trace the active circuit element from positive to negative, we take negative. Similarly, while tracing the passive element, if we trace the element in the direction of current, there will be a voltage drop and it is taken as negative. And if we trace the drop across the passive element against the direction of current, there will be a rise and hence that is taken as a positive. So with these assignments, if we write the Kirchhoff's loop equation for loop ABCA, we get I1 into R1 minus I5 into R5 plus I2 into R2 is equal to 0. For loop ACDA, we get minus I2 into R2 minus I6 into R6 plus I3 into R3 is equal to 0. For loop ADEA, we get minus I3 into R3 minus I7 into R7 plus I4 into R4 is equal to 0. And finally, for loop AEBA, we get minus I4 into R4 plus V minus I into R minus I1 into R1 is equal to 0. Don't you feel that the writing the Kirchhoff's current and voltage equation for the junction and for the closed loop is so easy and clear? I am sure you have understood these concepts very clearly and you see that you practice writing these equations properly, number one. And number two, if you have any doubt in identifying the junctions, branches, loops, I suggest you observe and see my video on network terminology. Further, in Facebook, I have already posted the self-assessment test and you can take up that test and find out how much that you have understood about writing the Kirchhoff's current law and writing the Kirchhoff's voltage law. Thank you very much for watching.